All right, let's do some more of the multiple choice questions here. We did this one already in class, so I'm going to go to 5. This is a related rates problem. I tend to like them, but you need to. Um, so related rates problem is essentially very similar to implicit differentiation because what you do is there are several things are changing at the same time here, and we're supposed to find out how the volume is affected and what the formula is for the volume change. So we start with the formula for the volume, which is volume of a cylinder. It's given over here, right? Pi r square h. So pi r square h, and then we're going to rewrite it so that all variables that are changing are functions of time. So pi rt squared ht squared. Then we're going to differentiate the whole thing with respect to t. So we get, actually, let me use Riemann notation for this. You can use dash notation too, it doesn't really matter. But over here we have dv dt is equal to, let me start with this. So we're going to use, sorry, there's a mistake here already. There you go. That's just h of t. So we have a product rule here, right? Let's do this. Let's consider this here the first function and this the second. So we're going to take the derivative of this by taking, let's take the first function original first. So it's going to be pi rt squared times the derivative of the second function. That is h, can't think yet this morning, dh dt. And then, so this is the first part of the product rule. And then you go plus, and here you take the second function in the original, so that h of t and the first function's derivative. So that is 2 pi, so times 2 pi r of t, and then dr dt, because you have the inside function here is r of t. All right, so now we have everything we need. Now that we have everything we need, we can just take out all the t's and replace the dh, the different, these guys here, the derivatives, with the actual rate at which they're changing. Okay, so we get dv dt is equal to pi r squared times dh dt. dh dt is the radius, the height of the cylinder is decreasing at a rate of 5 units per second. So it's going to be -5. And then the second part is going to be, let's order this in the normal way here, 2 pi r h, right? 2 pi r h. And then this is the rate of change of the radius. That's 2 units per second. All right. Now we pretty much have everything in place. Let's just clean it up and put it in the order that looks like they have over here. So this is 4 pi r h, 4 pi r h minus 5 pi r squared. So is this a solution? Yes, it is. It's solution number C. Okay, beautiful. That one's done. And let's see about this one here. Oh, so this is a conversion between definite integral notation. Let me put some numbers on here, 5 and 6. So this is a conversion between definite integral notation and the notation as an infinite Riemann sum. So in the infinite Riemann sum, we have one factor in here that represents the width of the slice, and that's this thing here, right? That's this factor right after the sum sign. It can be in front or after the actual function sign, and then it's a function that represents the height of the rectangle, and that's inside. That comes from putting an expression that is depending on the count of the slice in the progression here in the sum into the actual function. So the actual function is obviously square root of x. So this expression here is what that is, right? And what we have is we always have to have an offset there, right? Because I have a bunch of slices like so, and the beginning point is always my starting point. In this case, it's 2, so it would be a in a normal in a general way of writing it. And now I get to this x by taking the width, which is the same as the width of in the front here, by taking the width and adding the width to the starting point of the integral as many times as I'm in the iteration. So that means essentially this thing inside here has to be, it has to include the starting point. So it has to be one of these two. And then it has to be the same as the thing in the front. So that would be either 4 over n or 6 over n. And then it has to be multiplied by the iterator, okay? So both of these would be good. Now let's see if it's 4 or 6. What determines that? Well, the width is determined by being, a slice, a fraction over n, a fraction of the width of the integral. So it's going to be the top of the integral minus the bottom of the integral over n, and the n. So that n. So that makes it then 6 minus 2. So that means it's 4. So that means we're looking at C again. Okay. So you can write this out formally here. If you recall this generic format here, a integral from a to b of f of x dx in infinite Riemann sum notation is the limit as k, let's stick with k here, goes to infinity of the Riemann sum from which uses k equals 1 to n. So now I'm switching around this. All right, let's see. That's not where the k goes. So the iterator is just a number n that goes from, that determines the endpoint here, right? How many slices I have in that, and the limit goes to that. So it puts that to infinity because I'm going to go towards infinitely many slices in this sum. Okay, then k is the iterator. So k is the value that this takes on, the formula on the inside takes on for every time you increase it by 1. And then you increase it by 1 until you get to n, and n goes to infinity. So So then we have b minus a, let's write it in the same order as that, over n times f of, that here is going to be the starting point plus b minus a over n times k. Yeah, there, it's a little tightly here written, but so there you go. So this here is then the same as this is AB. So we've identified C. Let's call it good for that. All right, now this here, figure above shows a graph, the continuous function g in the interval 0, 8, that h be the function defined by integral that has g of t as the derivative. So that means h is the accumulation function under this graph. And we're starting at 3 at this point right here. Well, what intervals is h increasing? So this 3 here is a red herring. That doesn't matter because you're only going to look at this being the derivative of h. Okay, g is the derivative of h. So if you only have to say, answer this question on what intervals is h increasing, you simply look at the graph of g, and wherever it's above the x-axis, that's where it's increasing. So it means h is increasing from 0 to 1 and from 3 to 7. So C is the correct answer on that one. Next, so it's good that some of these multiple choice questions really only take under a minute to solve, and you don't really have to show any work if you right. So you could say for this here to show your work, you could say h prime of x is equal to g of x, and therefore when g of x, or you write out h is increasing where g of x is greater than 0. So that's C. All right, so let's see what this is. It's an integral problem. We have to actually find that integral here, and that's an indefinite integral, so that goes, no, has no boundaries. 1 minus 9x squared dx, and this one we're going to solve this by using u substitution for the thing that's under the square root, because this x squared here is going to be part of the, or I should say that x here is going to be part of the derivative of u if we choose. So you say let u equal to 1 minus 9x squared. That means du is going to be negative 18x. Yeah. And dx. And so here you see x dx is going to be that. And that means if you just want to isolate x dx and just create the thing here that's going to replace everything that you need to replace, you could just divide both sides by negative 18. So you would get negative, let's do it this way, write it this way. It's going to be a little cleaner later. Negative 1/18 du is equal to x dx. You see now you have exactly what you're going to need to replace here, substitute. Okay, now you're going to substitute it. So we're going to have x dx. So let's pull, first of all, let's pull that negative 1/18 to the front. I'll show you in a minute where these two steps are the same. So that, and then you have left du over root u, okay? So now you're doing the antiderivative. Antiderivative of 1 over square root of u is going to be, let's do this by calling this negative 1/2. So add negative 1/2, add 1 to negative 1/2, and then divide by that. So negative 1/2 plus 1 is 1/2, and then divide by that. So it's going to be, the root is going to get to the top, right? Like so. And then you divide by 1/2, so it's going to be times 2. And don't forget the negative 1/18 in the front. Like so, okay? Now let me clean this up again. Do we have to have anything else? Well, we have to have the C. So let's write this clean and also just do the U substitution in reverse. So we're going to put this here, negative 18 times 2 is negative 1/9 times square root of, put this back in, 1 minus 9x squared plus C. And let's see if we have something like this here. Yes, we do. So that would be A. So A is the correct answer in this one. Let's do one more. Oh, okay. A slope field. So the slope field, we're looking for patterns and then just trying out if we get this pattern here by plugging in the y value and the x value into the different formats here. So the pattern that I see here right off the bat is a horizontal line of all slopes being 0 at 2 and also at -2. And then it looks like these here slopes at x equals 0 are all, looks like about -1. So let's test some stuff. So what happens is, regardless of the x value, if I plug in 2 or -2 for y, it's all going to be 0. So that kind of seems like I'm not going to be able to use this or that, because that would change x if y is 2. So these couldn't be it. They're only dependent on x. So you can't have a horizontal equality here of gray. And if you look at it now, pretty much all of the slopes are identical for a specific value of y. So that means the differential equation here can only be dependent on y. So it has to be A or B, and now I can just try out what happens. 2 turns this one 0, but negative doesn't. Negative would be -2 for this. 2 turns this one to 0, and -2 also turns this one to 0. So this is the one. So B is the one. So what do we have here? I think for 10, we need to make a little sketch. We have x equals e to the y. So it goes to 1, e to the y. So it goes like so. And then x equals 10. y equals 1 and y equals 2. So it's this area here, 1 and 2. So 1 and 2 are going to give me the boundaries of the integral. So I'm integrating this way, right? And the line 10 is on top or further away from the axis, so from the reference here, y. So it's going to be this minus that, e to the y, dy. Do we have one like this? Yeah, this one right here, right? C. All right.